In a previous lecture, a couple of weeks ago, we've already discussed the basic definition of an isoparametric element formulation. Now, isoparametric elements are special description or formulation of elements in which the same set of parameters are used to describe the geometry of the part or the element as well as the behavior of the element. That means we will have the same shape functions to describe both these properties. So it's as you can already imagine that you have already been defining the behavior of an element by means of a shape function, so forth. That means if you had u is equal to ni ui plus nj uj plus nk uk, that was the definition of the behavior in terms of the shape functions. And now if you want to have an isoparametric element, then you will also be defining the geometry, for example, the direction x, where an unknown location or just a general location x would be given as nixi plus njxj plus nkxk, something along the same lines. Now, it's very easy to say this. However, to apply the isoparametric formulation, we also have to understand why we need to do it, because there are some changes that we need to make. So the isoparametric formulation is not easy to apply, as you can imagine, in the standard coordinates, because a lot of things are changing, because everything has to be applied in the same shape function. And it doesn't mean that we have to always mesh a part such that this becomes an inherent property of the element. So we should be able, in principle, to go from an element which sort of looks random like this one to an element which takes exact rectangular shape, something like this. So what we want to do is that, first of all, we want to enforce a condition such that this particular element, I, J, M, N, has can be described by changing by description of a shape function such that we have the same description of the edge. However, it looks slightly different. That means it now starts looking perfectly rectangular, such as this. So the change we need to make, therefore, is to go from, let's say this is length L1, is to go from limits 0 to L1, in this case, to limits -1 to +1. That means we can make it uniform. And if we apply the same conditions to all the different edges, then we end up with such an element described in the natural coordinates, where we can move from -1 to +1. So if we have I, J, M and N as the nodes of this new element, which is described in the natural coordinate system and is also isoparametric, then we will be able to deal with the change just by means of a simple transformation, which we will discuss about in this video. However, we also need to describe the isoparametric nature of such an element. So let's say that we have already, this element is the same as the one that we have already discussed about before, that the quadrilateral element that we already derived the shape functions for. So let us assume that there is a certain load acting on this element and it reacts with a displacement field in a standard solid mechanics problem. That means if we do have certain degrees of freedom that are acting at these elements at each of the nodes, then we can write them as, here we have ui of x, here we have uj of x, here is um of x, and here is un of x. And in the same way, in the vertical direction, we have ui of y, here we have ui of uj of y, here we have um of y, and here you have un of y. So everything in the x direction is described with u as a standard formulation, ue, and anything in the y direction is described with v of the element. So considering this condition and that it is isoparametric, we will be able to arrive with the displacement field and the geometric field for this element. So I want to write it on the next page. So I say the displacement field for that particular element in 2 dimensions can be written as u of the element is equal to ni ui of x plus nj u j of x plus n m u m of x plus n n u n of x. And at the same time, in the direction y, I have v is equal to ni of ui of y plus nj u j of y plus n m u m of y plus n n u n of y. So that's the displacement field. We can also write this in a compact form as u v vector is equal to the matrix ni 0, nj 0, nm0, nn0. And in the second one, I have 0 ni, 0 nj, 0 nm, 0 nn. And that will be with u I of x, u I of y, u j of x, u j of y, u m of x, u m of y, u n of x, and u n of y. And then you have an entire vector so this uv is written in a matrix vector formulation. Now, when we have been talking completely about isoparametric elements, we also, now since we know the description of the displacement behavior for the isoparametric formulation, we can say that the description of the geometry is same as the description of the unknown behavior, which is the displacement field. Therefore, we can also write x and y, which is describing the geometry of the element, to be equal to the same description as we have here, an nn0, 0 ni, 0 nj, 0 nm, and 0 nn. And the only thing, of course, that changes also on this side is the x I, y, I, xj, yj, which are the coordinates, xm, ym, and xn, yn. And that is the geometric description in terms of the same shape functions as the behavior of the element. That means now we have described a basic isoparametric element in a rectangular format. That means we moved from an arbitrary element shape into a rectangular element shape by enforcing natural coordinates. Therefore, there is one kind of transformation that needs to be done, which we need to find out. And secondly, when we describe it as an isoparametric element, then not only do we describe the unknown behavior of the element by means of shape functions, we use the same shape functions also to describe the geometry, making it isoparametric.